Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out a few numerical examples on thin cylinder. Let us start with an example. A thin cylinder, 300 mm internal diameter and 10 mm thick wall is subjected to internal fluid pressure 6 megapascal. Find the longitudinal hoop stress and maximum shear stress induced in the cylinder. So you are given the internal fluid pressure as 6 megapascal and internal diameter is 300 mm and thickness of the wall is 10 mm. So it is already stated as a thin cylinder, so you need not check the conditions. Okay, so usually the condition check will be internal radius. You should take internal radius is 150 mm and 1/10 of the internal radius is 15 mm, and if the cylinder wall thickness is less than 1/10 of the internal radius, then you can consider it's a thin cylinder. You can treat it as a thin cylinder. In this case, internal radius is 150 mm, 1/10 of internal radius is 15 mm and thickness 10 mm is less than 15 mm. So here this cross check is not required because it's already stated as thin cylinder. Irrespective of that thickness, you have to treat this as a thin cylinder. Okay. Now to find out the longitudinal stress, you can use the PD/40 formula. Pressure is known 6 megapascal, that is 6 Newton per mm square, and diameter is 300 mm. Okay, and thickness is 10 mm. So you can substitute that. You should remember that this pressure should be Newton per mm square, diameter in mm and thickness in mm. So you get the stress as 45 Newton per mm square or 45 megapascal. So you got the longitudinal stress. Immediately you know that the circumferential stress is double of that, 90 megapascal, or you can use PD/2T, pressure into diameter divided by 2 into thickness. You'll get 90 megapascal. So one of these values, if you calculate for a thin cylinder, you can find out the other stresses. Okay, circumferential stress is 90 megapascal. Longitudinal stress is going to be half of that. Or if you find out longitudinal stress, circumferential stress is going to be double of that. And if you have to calculate the maximum shear stress is going to be half of this. Okay, or 1/4 of this, that is 22.5 megapascal. That is going to be the maximum shear stress. Okay, PD/80 is the formula for maximum shear stress. You can use that formula directly and get maximum shear stress as 22.5 megapascal. So these are the stresses induced on the cylinder walls. This is a maximum value. Any other plane if you take, you may have a different stresses. So maximum normal stress in circumferential direction is 90 megapascal, longitudinal direction is 45 megapascal, and maximum shear stress is 22.5 megapascal. Any other plane if you take, you may have different values of stresses. Let us work out another example. A city water pipe with 0.4 meter diameter supplies water at a head of 80 meter. Determine the thickness of the pipe taking an allowable stress for the material as 25 megapascal. Specific weight of water, it is 9.81 kilonewton per meter cube. So here you need to find out the thickness of the pipe, and you are given the allowable stress for the material 25 megapascal. So you are designing the pipe for its thickness, and the water head available is given 80 meter. This head will be creating a pressure in the pipeline, and usually due to the water head available, pressure can be calculated as gamma h. For example, if you have a beaker and fluid is available in this beaker, fluid is present in this beaker for a height h, the weight of this fluid will be area of the base into height, that will give the volume. Volume into specific weight will give the weight of water. That is area into h, volume into specific weight. If you take it as gamma, gamma AH will give the weight of water in this beaker. So that weight is the force acting on the bottom of the beaker. So the pressure on the bottom surface will be weight divided by area. Weight is AH gamma divided by A, you will get H gamma or gamma H. So pressure is going to be gamma H. So pressure at the bottom of this beaker is gamma H. Similarly, due to fluid column, the pressure created at any depth is going to be gamma H. So if pressure here means you have to take the height above this particular point, okay, gamma into H will give the pressure due to this fluid column. Okay, absolute pressure will be different. Atmospheric pressure you should add, or if any other pressure is acting, that should be added. But due to this fluid column, the pressure is given by gamma into, that is specific height of that fluid into the height of fluid column above that. So that is fluid pressure. So here you have a water head of 80 meter, and we know that specific height of water, that is gamma. Gamma is, so you can convert this specific height 9.81 kilonewton per meter cube to, so 9810 Newton per meter cube. So you can keep it in Newton per meter cube. Okay, so 9810 Newton per meter cube, that is a specific height of water, and the water head available is 80 meter. So you can find out the water pressure as gamma H 9810 into 80. This is in Newton per meter cube and this is in meter. So you will get the pressure in Newton per meter square. So once you get in Newton per meter square, you can convert it into Newton per mm square. So meter is 10 raised to 3 mm. So meter square is 10 raised to 6 mm square. So 10 raised to 6, denominator 10 raised to 6 mm square. So 6 decimal places you should move. So here 3 plus 3, 6. So that is 0.7848 Newton per mm square. So that is the pressure of water. So in the pipeline there will be a pressure. So this data is given to calculate the pressure of fluid inside the water pipe. So once the pressure is known and the diameter of the pipe is known, and you have the allowable stress in the material. So this is a maximum stress per meter. Allowable stress means maximum stress per meter. And you know, in a thin cylinder the maximum stress is hoop stress. So other stresses are less than that. So if you limit the hoop stress to 25 megapascal, longitudinal stress will be half of that, 12.5, and shear stress will be, maximum shear stress will be 6.25 megapascal. So this is the maximum stress induced, and you have to limit the hoop stress to 25 megapascal. So pressure we got, maximum hoop stress is 25 megapascal, and diameter is 0.4 meter or 400 mm. Then you can find out the thickness of the wall. So diameter is 0.4 meter or 400 mm. Specific height is 9.81 kilonewton per meter cube or 9810 Newton per meter cube. Allowable stress is 25 megapascal. So this stress has to be taken as hoop stress, since its value is always higher in a thin cylinder. So hoop stress you can limit, sigma c is equal to Pd by 2T, and pressure we have calculated for this specific weight and head of water available. We have already calculated the pressure. So pressure is 0.7848, diameter is 400, and thickness you can calculate, and thickness is 6.2784 mm. So if the thickness of the pipe, if you use 6.2784 mm, the hoop stress will be limited to 25, and now the longitudinal stress will be 12.5 megapascal. So all stresses are less than the allowable stress. But if you decrease the thickness, the stress will increase. The effect of decreasing this value is to increase the right hand side. So the value will, sigma c will increase. So you cannot decrease the thickness below this value. You can increase the thickness. Increasing the thickness will always decrease the hoop stress. For a given pressure diameter, if you increase the thickness, the hoop stress will decrease. So this is a minimum thickness required to keep the hoop stress to 25 or allowable stress to be 25 megapascal. Let us work out another example. A water pipe with a 600 mm diameter supplies water at a head of 62 meter. Determine the thickness of the pipe required when a material having yield stress 200 megapascal is used. Given specific weight of water 9.81 kilonewton per meter cube and factor of safety 4. So it is a similar problem. Water is available at a head of 62 meter. The pipe is 600 mm diameter, and thickness of the pipe you have to calculate. For the water pipeline, thickness of the pipe has to be calculated. Here the yield stress is given and factor of safety is given. That is only difference. The other data is similar. So here yield stress means the material starts yielding at 200 megapascal. So it can be considered as a failure of the material. If the stress reaches to 200 megapascal, the material fails. It starts yielding. So you cannot allow the stress to go to yield stress. So you have to take a factor of safety of 4. That means you have to keep the stress 4 times less than this yield stress. Factor of safety 4 means you have to take the allowable stress to 4 times less than this. 4 times less than the yield stress. So yield stress divided by factor of safety will give the working stress or allowable stress in the material. So 200 by 4 will get 50 megapascal as the allowable stress or maximum stress that can be permitted when this fluid pressure is acting. So a pipe should be designed for a maximum stress of 50 megapascal. The data given is diameter is 600 mm, specific weight 9.81 kilonewton per meter cube or 9810 Newton per meter cube. Yield stress is 200 megapascal. So you can find out the allowable stress as yield stress divided by factor of safety, which will give 50 megapascal. Now this stress can be taken as a hoop stress in the thin cylinder, since the hoop stress is the maximum stress induced in a thin cylinder. So allowable stress is 50 megapascal. So you can find out the water pressure as gamma H. Gamma is 9810 Newton per meter cube into 62 meter is a water head. So you get the pressure as 608220 Newton per meter square. So Newton per meter square you have to convert into Newton per mm square. So meter is 10 raised to 3 mm. So meter square is 10 raised to 6 mm square. So 10 raised to 6 in the denominator. So you move 6 decimal places here. 0.60822 Newton per mm square. So that is a water pressure. So now you can apply the circumferential stress formula. Sigma C is PD by 2T. Pressure is 0.60822. Allowable stress is 50. So from this you get the thickness of the pipe as 3.649 mm. So that is the minimum thickness of the water pipe required to keep the allowable stress to 50 megapascal. That's all for today. Thank you for watching.